Okay, we're back with part B of problem 15 on page 818. After we found the Taylor polynomial degree 3, we're asked to use Taylor's inequality. So here's Taylor's inequality. I have to find the fourth derivative of the function and estimate and determine the upper bound of this function, of course in absolute value, keeping in mind that x minus 1 has to be less than or equal to. And we'll determine that in a minute. So in this problem, where is my previous page here? So let me just copy here 0.8 less than or equal to x less than or equal to 1.2. Remember, a equals 1. We subtract 1 from all three sides, minus 1, minus 1, minus 1. So this will be negative 0.2 less than or equal to x minus 1 less than or equal to 0.2. As we know, this changes into the absolute value of x minus 1 less than or equal to 0.2. Next, our next step is to find the fourth derivative. So here was the third derivative. Bring down negative 7/3 and subtract 1 from the power. So we get negative 56 over 81, x to negative 10 over 3, which basically changes into 56 over 81, and this is the cube root of x to the 10th power. For the interval 0.8 less than or equal to x less than or equal to 1.2, notice that since this function is decreasing, as x increases, this function is decreasing, at 0.8, this function will have an upper bound. Okay, in absolute value. So let me put the absolute value because we are interested in the absolute value. Good. So this will be less than or equal to negative 56 divided by 81 times the cube root of 0.8 to the 10th power. I calculated this and I got approximately 1.4545. Now, in order to estimate, here it is. Let me show the formula again. It's right here. Our m is this number, n plus 1, because we are talking about polynomial degree 3. So this will be 4 factorial, and this will be 4, and this will be x minus 1. So less than or equal to 1.4545 divided by 4 factorial, and x minus 1, let me write it like this first, x minus 1 to the 4th power. But this, we already determined it here, is less than or equal to 0.2. So this will be less than or equal to 1.4545 times 0.2 to the 4th power, and everything divided by 24. When I calculated this, I got 0.000096972. Okay, now the part C of this problem is asking us to graph. I'm on page 6. So in part C, it says, check your resulting parallel by graphing the absolute value of Rn. So remember what the absolute value of Rn is. Is the absolute value of the function subtracting this. I'm going to put 3 because that's what we're doing. So the absolute value of the error for corresponding to the 3rd degree polynomial, Taylor polynomial. So what do I plug in the graphing calculator to graph this? Okay, so what I have to plug in is the original function, if I can still find it somewhere in my papers. Yes. Okay. the function. So this is x to 2/3 minus. And now I'm trying to discover the polynomial. All this minus. Remember to change all the symbols here. -1 minus 2/3 x minus 1 plus 1/9 x minus 1 squared minus 4/81 x minus 1 to the third, and everything in absolute value. In order to cut back on time, of course, I entered this already in the graphing calculator before I started. So let me remove these two, the last two we graphed. Okay. And so we are graphing R3, and I have everything entered already, all this. And don't forget the absolute value. Where do you find the absolute value? Is in math. So let me do that first. So go to math, scroll to the right, and the absolute value is at the very top. So coming back here, we want to graph this. So we are really looking at 0.8 to 1.2. That's where our x is. Okay, so the viewing window will be between 0.8 and 1.2 with a scale of 0.2. Y minimum, we're graphing a positive function. I'm going to just give it -1 to see the x-axis. And the maximum, I don't know, but look what the Rn should be less than or equal to this, right? So how high do I go? Depends on this. So I'm going to say from -1 to maximum of 0.0001. And now let's graph. Did it take that? Negative, sure, of course. It's 0.8. Okay, let's see what else I did in the viewing window. From 0.8 to 1.2, yes. With a scale of, yes, y minimum -1, and y maximum okay, let me see. It's so small, yes, okay. Y maximum, 0.0006. Let's try that. Okay, okay, 0. Okay, to that. Graph. Okay, we're getting there. Okay, so I have to change the upper y. 0.0001. Finally. Okay, so we graph this function. Which function? This. Okay, it appears that the maximum is here. We did get a maximum and upper bound, but we may improve by looking at the graph, graphing it, we may improve on this. Let's see. So when I plug in 0, let's see how high is Rn, or R3 in our case. So second and graph, and I would plug in 0, and let's see what I get. So okay, 0.8 I meant. Sorry about that. 0.8, not 0, of course. The viewing window obviously starts at 0.8 anyway. That's how it's the interval given to us. Okay, finally. Okay. So as you see, we improved on this by looking at the graph. So let me copy down this number. So we got that R3 of x in absolute value, according to the graph, is less than or equal to 5 zeros. 0.12345328844. So 4 zeros, 4 zeros. Through our estimation, we got that the error is less than 0.00009, but actually we can definitely improve on it, as you see, from 4 zeros and 9 for 4 zeros and 4. So it appears that the error is even smaller than that. Okay, these are cumbersome steps. Sorry about that. Okay, moving on. The next problem, problem 16, on the same page, 818, and we have f of x equals sine x. They're telling us that a is pi over 6. They're giving us the 4th degree Taylor polynomial, and they're giving us x, of course, between 0 and pi over 3. Same steps, everything the same as with problem 15. So let's start with that. Of course, with the derivatives. This time we have to determine 4 or 5 derivatives, actually. So let's do just that. So first, f of pi over 6. When we plug in pi over 6, we get 1/2. And then let's find f prime of x, which is cosine x. So f prime of pi over 6 will be the square root of 3 over 2. Okay, we're moving on to the second derivative. The second derivative is negative sine x. So then the second derivative at pi over 6 will be negative 1/2. The third derivative is negative cosine x. And the third derivative at pi over 6 will be negative the square root of 3 over 2. Now the fourth derivative is sine x. And the fourth derivative at pi over 6 is 1/2. And we can just determine and be ready with the fifth derivative, which will be cosine x. And the fifth derivative at pi over 6 is the square root of 3 over 2. This is ready for part B. Okay, we're not going to use it in part A for the Taylor polynomial. Okay, moving on. My page 7. Good. So let's write T4 as 1/2 plus the square root of 3 over 2 over 1 factorial, x minus pi over 6 minus 1/2 over 2 factorial, x minus pi over 6 squared plus negative the square root of 3 over 2 over 3 factorial, x minus pi over 6 to the third power plus 1/2 over 4 factorial, x minus pi over 6 to the fourth power. Okay, let's try and clean it up a little bit. I'm going to move this page over. Good. So let's see what we get. We get 1/2. We get the square root of 3 over 2 and x minus pi over 6. We get negative 1/4 x minus pi over 6 squared. We get minus the square root of 3 over 12, x minus pi over 6 to the third, plus 1 over 48, and x minus pi over 6 to the fourth power. Okay. Perfect. So that is it. In part B, they're asking us to graph, and in part C to graph it, but in part B they're asking us to estimate this. So as we know, this is R4, which is the absolute value of f of x minus T4. Let's go back to the fifth derivative of x in absolute value, which was cosine x. And because this is definitely less than or equal to 1. And x is between 0 and pi over 3. So that's the definitely upper bound. Again, like before, we have to subtract pi over 6 in this case. So we subtract pi over 6, subtract pi over 6, subtract pi over 6. And we get negative pi over 6 less than or equal to x minus pi over 6 less than or equal to pi over 3 minus pi over 6 is pi over 6, because we need this for the remainder using the Taylor's inequality. So the absolute value of x minus pi over 6 is less than or equal to pi over 6. Okay, at this point we have R4 is less than or equal to 1 divided by 5 factorial. This is the m. Where is my formula? Where's my formula? Here it is. So this is our m, 1, because this is 4, this is 5 factorial. And this is x minus pi over 6 to the 5th power, but we already know that this the upper bound is pi over 6 to the 5th power. And if you calculate all these, you will get, I got 0.000327 Now let's see if we can improve on this with part C, with the graph. And yes, I entered this very cumbersome, and we know what you have to enter. The absolute value, don't forget the absolute value of the function, which in our case was sine x, minus this minus this plus this plus this minus this. I'm going to write it here, minus 1/2 minus the square root of 3 over 2 x minus pi over 6, but plus 1/4 x minus pi over 6 squared, plus the square root of 3 over 12 x minus pi over 6 to the 3rd power, and minus, so let me make sure that I put minus minus plus, yes, minus minus plus, and then plus and minus, correct. And the last one is 1/48 times x minus pi over 6 to the 4th power. You have to enter it exactly like this, and I did. Okay, so let me de-highlight this and highlight this. Sine x minus 0.5 minus, and so on and so forth. So now we are looking at a totally different viewing window. So we have 0x pi over 3. Okay. And of course, make sure that the mode is in radian mode. Okay. So here we are. Enter. Viewing window. Between 0 and pi over 3. I will put a scale of pi over 12. I didn't mean that. I meant this. Pi divided by 12. Okay. Y. Between 0 and 0.001. Scale of 1, that's fine. So let's see what we get. Again, it appears that at 0, the remainder, R4, is the smallest. We can check at both ends just to make sure, but it appears that it's the smallest here. So second, and so put 0, and let's also put pi over 3, and let's see what happens. So the first one is e to negative 4. Okay. 2.7. So R4 appears to be less than or equal to, okay, the first one is 0.123, 3 zeros, 2964. And obviously, we already improved on, with a graph, we improved on what we determined with the upper bound. And if we want to look at the other one, that is 0.000269. Still an even better improvement. So this was 2964, and this was 2679. Okay, so at pi over 3, so it appears that the remainder using T4, the error using T4 to approximate this function, using T4 to approximate this function, the error is even less. It's less than what we determined. We can always improve on. So we did at 0.002679, smaller than this. Okay, perfect. Moving on. This was 16. Let's move on to 21. Let's see how we are on time. Oh, I'll stop and start with the third video.